See people moving from the previous room.
Welcome everyone, and thank you for joining us today for our virtual event. My name is Dr. Colin Coates, and I'll be your host for today's presentation. In this session, we have the rather intriguing title, Operando Spectroscopy for Materials and Catalysis, Time and Non-Innocence. I'm joined by today's speaker, Professor Brown. Wesley Brown is from Sligo, Ireland, and completed his PhD thesis on the photochemistry and photophysics of ruthenium polypyridyl complexes at Dublin City University in the group of Professor Voss. He held postdoctoral positions at Queen's University of Belfast with Professor John McGarvey and University of Groningen with Professor Feringa. In 2007, he was awarded the Vidi Innovational Research Grant, and in 2008, he joined the faculty at the University of Groningen as assistant professor. He is currently full professor and chair of molecular inorganic chemistry at the Strating Institute for Chemistry. His research interests are in the application of spectroscopy, and especially Raman spectroscopy and electrochemistry, to bioinorganic catalysis and molecular-based material science. So welcome, Wesley. Just a little housekeeping before we get started. You've all joined this presentation in listen-only mode. If you have any questions during the presentation, please type them into the question box in the control panel as we go along. Questions will be answered at the end of the presentation. Now, without further ado, I'll hand you over to Professor Brown.
Thanks, Colin. Unfortunately, after talking to you for a few minutes, I'm probably going to give this in a Northern Irish accent. So apologies for anyone who doesn't understand me. I'm, of course, from the west of Ireland, but I'm currently in the University of Groningen in the Netherlands, and I've been here for the last 20 years, so I get the hard chi in the word. I have to get a little bit used to this interface as well too. There's the next slide. So what I'm going to talk about today is about operando spectroscopy for materials and catalysis. I'm really going to go through one or two examples and give you some of the experience that we've gained in our lab over the last few years, and also try and highlight the flexibility of especially Raman spectroscopy for studying catalytic systems of various types. So, okay, so what I want to do is I want to make connections between material science and catalysis, and I really want to show you how we have been approaching extracting information on reaction progress with spectroscopy. And it's really, the operando is, are you looking at your reaction as it's going on in real time? But more to the point, is everything you see going on really what's going on? So to try and illustrate some of the problems or challenges and opportunities you'll have at Raman spectroscopy and spectroscopy in general in following reactions, I'm going to focus on two transition metal catalyzed reactions. The first is an iron catalyzed reaction, and it's actually from my colleague Ben Feringa all the way back in 2001. He used this rather intriguing complex, which is a phenolate-based iron complex. Beautiful colored compound, nice purple color, two oxidized alcohols to ketones. This is done with hydrogen peroxide, and this is not a very useful reaction per se in terms of the turnovers and efficiencies and everything. You see 4% yield, but an intriguing reaction to figure out how this catalyst is actually working, and I'll come back to that in the start of the talk. The second part, I'll actually move on to something which you'd be more familiar with, believe it or not, especially if you have a dishwasher and you use sun tablets. It's actually this catalyst which you see on the top. I'm not sure if I have a laser pointer, if you can see anything, but I'm pointing to things, so you can use your imagination to where I'm pointing. The catalyst on the top, this manganese catalyst, is used. It's the red flecks that you see in sun tablets. It's a catalyst which was originally used for washing powder and is now used in dishwasher powder just to make everything brighter and cleaner. So I'm going to tell you two little stories about this, and I'm going to focus on the spectroscopy rather than on the chemistry itself. So first of all, why would we want to look at an iron complex like this? Well, it is a mimic for the catalytic site of glucose oxidase. It's a functional mimic in the sense that it has a phenol unit which is redox active. And the idea is that the redox active nature of the ligand would impart extra reactivity to the iron center to do an oxidation chemistry, which is essentially redox chemistry. So I'm going to focus on the kinetics, what happens during this reaction. Now, it's an intriguing reaction because if we actually follow the absorbance, so the color of the solution over time, it gradually fades to a kind of a yellowy color over a period of about an hour or so. I just clicked a button. I'm not sure if I do. Yeah, here it goes. And if we actually follow the turnover, sort of how fast the reaction proceeds, so at what point the reaction kicks off, it goes fairly slowly at the start and then accelerates and then stops. And it stops roughly at the same point that the color is gone. Now, a remarkable effect is if you see with the triangles, such as this very short line, which you see at the start, if you add triflic acid to this catalyst and then do the reaction, it goes immediately and very quickly. So there's an idea that the addition of acid, for example, breaks up this mu-oxo bridge, which is between the two iron centers, and that kick-starts the reactivity of mononuclear iron complexes. Okay, so what do you see in absorption? Well, here's the absorption spectrum of the iron complex. It's got an absorption around 590, 580 nanometers. And if we add acid, that absorption shifts and we get this very odd blue colored solution. And that gives an indication there's a change in structure of the compound upon protonation, and the complex then becomes more reactive. You can imagine if you put a proton on top of that oxygen between the two irons, it would be easier to break up the complex. So here's a model for what's going on. We add triflic acid, we get a mononuclear complex. That mononuclear complex can then exchange an hydroxy ligand for hydroperoxy, and the hydroperoxy then is responsible for substrate oxidation. Okay, it's a nice model. One problem is that if we add hydrogen peroxide, it's 50% volume and water at the maximum. And that means a lot of water is added to the reaction. And water has an effect on triflate because triflate is a very strong acid. But if water is present in acetonitrile, you have the leveling effect. And then the strongest acid you can have is a hydronium ion. And that actually shifts back the equilibrium back to the original compound straight after the hydrogen peroxide is added. And then the rest of the reaction continues under relatively non-acidic conditions. So how do you study such a reaction? Well, probably the easiest thing is to follow the reaction over time and see how its spectroscopy changes. Now, if we follow the reaction over 20 seconds with acid present, we get this nice yellow absorption, which is not very, featureless essentially. And, well, there's not really much we can do to study this compound because you can't isolate it from the solution. There's too many components in there and it's present at such a low concentration. Isolation is not practical. And it's EPR silent. So we know it's not a mononuclear iron 3, typical iron 3 complex. It's likely to be an oxo-bridge dimer in the iron 3 state. But so was our original compound, but that was nice and purple. So how do you study such a thing? Well, one trick to do is to use a technique called resonance enhanced Raman. So we run a Raman spectrum with an excitation, which is resonant with an absorption band. And I'll come back to this a lot. And because of that, even something present at a very low concentration, there's a chance that its Raman modes will be enhanced quite dramatically. Sometimes you hear quotations of 10 million times, but in the case of inorganic compounds, it typically is 50 to 100 times enhancement, which is just enough to get a 1 millimolar solution of something up to the level where you can start detecting. And when we do that, we run a Raman spectrum at 355, which you see below the absorption spectrum. That actually corresponds to something we looked at before, which is a very similar complex, which doesn't have these phenolate units, and it's a bit boring. And this is a relatively unreactive iron dimer. So this is what appears 20 seconds after the reaction starts. And if we look at the profile, well, within the first, let's say 15 minutes, we see conversion. So our catalyst has undoubtedly changed structure in the first 20 seconds and thereafter does the catalysis. So we have two questions. What is happening in that first 20 seconds? And secondly, what actually is doing the catalysis? Now, we can follow by UV-vis spectroscopy with fairly high time resolution. And well, every 0.1 of a second or every half second gives us enough time resolution to see that our initial very broad absorption, as soon as we add the hydrogen peroxide, we see a very broad increase in absorbance over the entire spectrum. And within a few seconds, we see a decrease. And then there's appearance of a band around 600 nanometers, which then decreases itself to give us this final spectrum over 20 seconds. So we have very little time to catch whatever species are present there. But if you look, there's no isospecific point, and that means there's multiple species forming at different time stages in the reaction, and with varying concentrations and various spectroscopic properties. So it gives us a bit of a challenge to understand what's happening in this reaction. So we have to be quick. So if we take a laser at 532 nanometers to run a Raman spectrum, hitting into this absorption around 600 nanometers, or around 560 nanometers, And we record an EPR spectrum of the sample, which is flash frozen. So we freeze the sample after 20 seconds or within 20 seconds. So you add the peroxide, mix, and then quickly freeze. You quench, you stop time essentially in the frozen solution. You can run an EPR spectrum. The EPR spectrum tells you this time we have a low spin iron 3 hydroperoxy. So these signal at around 2.12 is typical for a low spin iron 3 peroxy. We have a lot of high spin iron 3 as well too, but we happily ignore the huge signal and look at the small signal. And if we look at the Raman spectrum, it's difficult to believe, but it is very reproducible, and we can use labeling to establish the bands are what we think they are. We actually see the bands which are very characteristic of an iron 3 hydroperoxy. So we know that after about 4 or 5 seconds, the predominant species in solution, or one of the species in solution, is an iron 3 hydroperoxy, and thereafter it goes to an iron 3 dimer, which is essentially inert or inactive from a spectroscopic point of view. So the question is, what are these very strong absorption bands that appear during the reaction? Now, the catalysis is done with 2 equivalents of trifluoroacetic acid with respect to the complex and 100 equivalents of hydrogen peroxide. And this actually confused us for quite a while. Imagine a year and a half of a student working on this, until we just decided, well, what happens when you add 1 equivalent of hydrogen peroxide? If you don't add the acid, nothing happens. But if you have the acid present, something happens. So what happens? Well, you see new species. So we monitor 785 nanometers, which is resonant with these very short-lived absorption bands. But bear in mind that this absorption at 785 or around 800 nanometers is only there for the first few seconds. So we have 3 or 4 seconds in which to get spectra. And we can do that. And we actually see that, well, if we look initially, we see very weak signals from our catalyst, which are resonantly enhanced. And we see a very large jump in intensity of some bands, which are in an intermediate, which are quite characteristic of a phenolate, an oxidized phenolate unit. We can actually follow over time. And to give you an idea of what the challenge is in this case, well, if we look at the intensity over time, we see 2 things. Well, first of all, we see the sudden spike in signal intensity, and that corresponds to the intermediate, which is labeled in the graph beside. And the second thing is the hydrogen peroxide signal, well, it jumps up initially because we've added hydrogen peroxide. And that's a non-resonantly enhanced signal. So that's actually quite a high concentration of hydrogen peroxide, 100 equivalents. And then that slowly decreases over time. So it's not that we have this very rapid reaction and all the hydrogen peroxide's gone. No, we have a very rapid reaction. A new species appears. It has a new resonantly enhanced Raman spectrum and then disappears within a few seconds. Now, we're acquiring a spectra every 300 milliseconds or 200 milliseconds. And that's about as high a time resolution as we've gone so far with this system. We can go faster, actually. It is possible to go faster with reasonably low power lasers. But what you notice is the spectrum is very jumpy. And you see there's an increase and a decrease in the signal. That's not because of noise in the system. It's actually due to the fact that when you add the hydrogen peroxide and water to the cuvette and you have mixing, it actually takes about 1.5 seconds before you get full dispersion of the hydrogen peroxide in a cuvette. So what you're seeing is a variation of concentration in the confocal volume in the field of view of the probe as the hydrogen peroxide is moving through the solution and dispersing. So it's one thing to watch out for when you're doing very fast reactions, especially with stop flow. Mixing is one difficult issue when it comes to doing very high time resolution of these sort of reactions where you start the reaction by adding something. Of course, if you want to see what's happening and you want to slow things down, you say, well, add less hydrogen peroxide. And that indeed was the suggestion I made a few years ago to the student. And then something funny happens. Well, what we see is much more dramatic changes to the absorption spectrum with 2 equivalents of hydrogen peroxide, so not under catalytic conditions. And if we look by absorption spectroscopy, we can start pulling out kinetics of species appearing and disappearing. But we can also do resonance Raman spectroscopy, so take a laser 785 or take it at 488 or 473 nanometers, 457 nanometers, depending on which wavelengths you have available, and hit into different bands. And what we see is 2 very distinct spectrum. At 785 and at 473, we see 2 spectra which are very similar, but similar doesn't mean the same. And a Raman spectrum is a manifestation of structure. So if the Raman spectrum is not the same, it's not the same species. So we are actually looking at 2 very similar but different species. Question is, what are they? One other thing to notice is if we follow the Raman intensity over time and take into account inner filter effects, remember there's a very high absorbance here, so your Raman intensity will be affected by inner filter effects, so you have to take that into account. We actually see very different kinetics than we get by UV-vis absorption. And the good thing about Raman spectroscopy is you look at individual bands. You can pick bands which don't overlap, whereas with absorption spectroscopy, you get a lot of overlap between different bands. So following by Raman spectroscopy actually gives us a proper insight into what's happening during the reaction. Now, if we add more than one equivalent, and I see that there's a window which is hiding my screen. Move it over. Sorry, if we add an equivalent of CAN, cerium ammonium nitrate, that's a one electron transfer oxidant. So not hydrogen peroxide, it's really one electron is taken off the compound. We see similar changes. Now, you would agree that the absorption spectra are not exactly identical. There are some similarities, but you wouldn't say they're the same. However, if we follow the Raman spectra that we get at 785 and 473, we actually see that the Raman spectrum we get with hydrogen peroxide are identical to the Raman spectrum we get with an electron transfer oxidant. What this means is what we're seeing with hydrogen peroxide is a one electron or two electron oxidation of the complex. So that gives us insight immediately from the Raman spectra, allows us to compare different situations, and allows us to tell start to tell what's going on in this reaction. Now we take a step back and we look at this complex and we compare it to a complex which has got these tert-butyl groups on. Tert-butyl groups are quite handy because they don't really affect the chemistry of the compound per se. It's still catalytically active, a little bit less catalytically active, but the tert-butyl groups block reactions of the phenol unit, such as dimerization or coupling, which gives you a hint of what's coming. If we look at the voltiovoltammetry in acetonitrile, well, we see that with the tert-butyl groups, you get very nice reversible two-electron oxidation steps, whereas without the tert-butyl groups, we get irreversible oxidation. If we look in dichloromethane, and this is kind of the chances, an important aspect in research. Just by chance, we decided to use dichloromethane because we wanted to go to low temperature, around 200 Kelvin, to do the electrochemistry, to try and slow down the degradation processes to lead to irreversibility. And it should have worked fine. We go to dichloromethane because there's a much lower freezing point, so we go down to 200 Kelvin, where acetonitrile doesn't. And that was quite fortuitous because we don't lose the irreversibility, we get a very different irreversibility. And we see oxidation of the complex followed by something appearing on the electrode. So we get a buildup of a film on the electrode. Now, my research group is also very busy with electrochromic materials, and we recognize this immediately as electropolymerisation. And you see a buildup over multiple scans of this film on the surface. What's actually happening is that the complex is being oxidized. We have a radical character on the phenol unit. You get CC coupling, loss of protons, and you get a bridge between two complexes. And of course, you can build up the bridge in a long chain, and that becomes an oligomer or polymer on the electrode. So that means we have this sort of compound on the electrode, these biphenol units, and we can oxidize and reduce them reversibly. It's quite a stable oxidation and reduction. Now, using microscopy and using a microscope at 488 nanometers and 785 nanometers, we're able to look at these thin films which appear with these thin films using a spectral electrochemistry. And when we do this, we oxidize to the first oxidation and second oxidation, and we look at how the absorption spectrum is changing. We see there's an appearance of a band at 870 and appearance of a band at 475 when we go through the first oxidation and second oxidation. So we can really understand really what species are responsible for these. And if we look at the Raman spectra obtained at 785 and at 473 nanometers for these species, we compare them with the spectra we obtained with cerium ammonium nitrate or what we were obtaining with hydrogen peroxide, we see they're identical. And if they're identical, it means the same species. So this allows us to understand in this system, so the combination of looking at the complex as a material and not just as a catalyst, we can actually see that the electrochemical the first step that's occurring under catalytic conditions is we're oxidizing the iron centers, but really we're oxidizing the phenol centers. They're undergoing a polymerization to form a series of mono and dications, which give distinct absorption spectra. And that happens in the first 2 or 3 seconds of the reaction. Then we have a follow-up reaction, which the phenolate unit is actually cleaved off. And this is a known reaction in organic chemistry where you actually cleave off this amine phenol unit by oxidation. And then we're left with a complex which doesn't have this phenolate unit, and it's that complex which engages in catalytic activity. So you can't actually make this complex directly because that NaH prevents you forming complexes, but you can make it by degradation of the phenolate complex in the first place. We have similar complexes where the X, which is shown in the middle structure, is a methyl group, and they give very similar spectroscopy and catalysis that we see with this complex. So what I wanted to show you there is by actually following reaction at different timescales and looking with different spectroscopies, we can start building up a big global picture of what's going on in the reaction. But it's also important to remember that these very large changes we see at the start of the reaction are due to a change in the catalyst structure, but don't actually tell us much about how the catalytic activity is, well, what's the cause of the catalytic activity that we observe. So you have to be careful. Just because it's very exciting spectroscopy doesn't mean it's as relevant to the problem you're working on. So the second problem I'm going to introduce relatively briefly is Lewis acid activation of transition metal oxidation catalysts. And it works on theory. So the idea is you take a Lewis acid, and a Lewis acid will react with your compound to enhance a change's properties. So where does this come from? Well, the idea is not very new. The idea comes from quite a long time ago on studies of photosystem 2. And if we look at the oxygen evolving complex of photosystem 2, you'll see that there is a cubane structure. Originally, the idea was there was 4 manganese centers in this cubane, but it turns out there's a calcium ion sitting in the cubane structure and not a manganese ion. And the calcium is acting as a Lewis acid. You can replace it with strontium, it still works, but if you replace it with other Lewis acids, then you lose your oxygen evolving ability. So it's a pretty critical structure. And you can imagine that, well, I think everyone knows that photosystem 2 has been the center of attention for many years for a very large number of researchers. Of course, in biomedical chemistry, we like to build structures which mimic this sort of calcium binding to oxygens as Lewis acid activation or Lewis acid change in properties of a multinuclear complex. And as an example of it, this comes from the group of agapi. It's a tri-manganese complex. And if you start changing the Lewis acid, which is present in solution, which binds to 2 oxygen centers, you can actually have a very large effect on the redox potential of this complex. So Lewis acids really can affect the potential or the reactivity of complexes, especially multinuclear manganese complexes and iron complexes. So the question comes, can we use Lewis acids to our benefit in catalysis? And if you know Beveridge's law, well, you know what the answer to this is. I'm going to give an example of this complex. This is the bis manganese 4 complex, which was developed by Carl Vickard all the way in the 1980s, in the efforts that were going on then to actually build structures which mimic photosystem 2 to help us understand how photosystem 2 works. Of course, at the same time, Unilever were searching for catalysts which could improve laundry applications, which seems a bit far from photosystem 2. And they were screening pretty much every compound or catalyst they could find around Europe at the time. And Carl Vickard's group submitted several samples of compounds which were tested. And it turns out that this complex was extremely effective at cleaning clothes, at removing especially, I think, tomato stains and tea stains from clothes. And it works wonderfully. I can actually tell you this because I have some samples and I have used it occasionally myself in washing applications. Proctor Gamble claimed that it gave cotton damage, and it does give a little bit of cotton damage, but not as much as claimed. But it was withdrawn from use from laundry products very quickly. Of course, dishwashers don't have the same problem with cotton damage, so kind of a second life for this catalyst was its use in helping to clean off stains on plates and that in the dishwasher, and it actually works very well. And probably most of you at some stage have used these dishwasher tablets or have been in a household that's used them, so you are all familiar with this catalyst. But maybe something you didn't know about this catalyst is it's actually a pretty useless catalyst for oxidation chemistry. And one of the problems is it is very effective at decomposing hydrogen peroxide. In fact, it can do it quite violently, and I'll come back to that. It does oxidize alkenes, and from an industrial point of view, from a chemicals point of view, this is of interest. And after the use in laundry applications, it was also applied for alkene oxidations. So, as I said, the problem is hydrogen peroxide decomposition, which on large scale is potentially risky because you generate lots of oxygen, which is a gas which can cause things to blow up. So we don't want to do that. And a lot of effort has been focused on finding additives or finding some sort of conditions which suppress the peroxide decomposition and enhance the oxidation capacity. So early in the noughties, we were working on this. Our group with Ronald Hache, who was one of the first to work on with Unilever on the laundry applications, we, together with Ben Feeringa, well, we kind of discovered, worked out by actually following this reaction. As a whole story to this as well too, that carboxylic acids were very effective at preventing hydrogen peroxide decomposition and actually allowed you to steer the chemistry of the reaction between epoxidation and dihydroxylation. So there's quite a story behind the use of these acids, but that's quite a long time ago. What tweaked my interest recently was a report by Watkinson and a parallel report by Yin, where they very elegantly showed that if you use scandium and other Lewis acids, you can actually improve the properties of these catalysts and get very good turnovers for epoxidations of styrenes, which are an important epoxidation to do, and very fast reactions. And this just tweaked your interest because, well, first of all, why didn't we do it? Of course, that's always what you think, why didn't you try it yourself? But other things, how is it working? How is scandium actually delivering this? So we decided just as a Friday afternoon experiment to start taking a look at this. And of course, like most Friday afternoon experiments, it goes on for months afterwards. But we're also in a hurry to get our results. So we don't like using gas chromatography or HPLC or anything to follow reactions. We tend to use Raman spectroscopy. And it is a Friday afternoon. And you can tell it's a Friday afternoon. And I'll tell you why from the spectrum. So this is a Raman spectrum of solution of styrene, which is going to be converted to epoxide with this catalyst and scandium present. And we have hydrogen peroxide. This is just a Raman spectrum of 785 nanometers. And what you can see at around 1600 wave numbers is the bands from styrene, which are decreasing. That allows you to look at conversion. And the band at around 1260, you see with an arrow pointing up, is from the styrene epoxide. We can see the epoxide formation. And at around 870 nanometers, you can actually see the band from hydrogen peroxide. So you can follow the hydrogen peroxide appearing and disappearing. So when you add it, it goes up and then it disappears over the reaction. What you also see is a few dips. These are room lights because the reaction was followed over time. And someone decided to turn off the fluorescent bulbs or fluorescent room lights halfway through the reaction. And of course, a background had been taken on with the room lights on. So these are negative lines, but that allows you to check what time people went home. I'm only kidding, we don't do that. So one of the things that was noticed by the student who was working on this was you get a lot of hydrogen peroxide decomposition. And when they meant a lot of hydrogen peroxide decomposition, what they meant is that the sealed cuvettes that they used for following the reaction exploded. So the whole cuvette exploded, which is not something you really want to do. But of course, just because a cuvette explodes doesn't mean it's hydrogen peroxide decomposition to oxygen. You could have other gases involved. And that's going to make a little aside to this. You can actually follow the gas evolution over time using Raman spectroscopy if you have two different laser wavelengths, or even the same laser wavelengths would work as well too. We take a 785 nanometer laser probe just to follow what's happening in solution, how much hydrogen peroxide is present, how much catalyst. But routinely, we actually use a 532 nanometer laser to look at the headspace above the reaction in the cuvette. And if the cuvette is closed, and if you're a little bit careful, you have to be careful. And if you're going to do this, you can just drop me an email afterwards. I can give you some tips on it. And you can actually follow the concentration of oxygen in the headspace. And here's an example from an iron complex we're looking at. You see that there's a nitrogen band around 2329 and an oxygen band of 1555. Of course, you have oxygen present because it's 20% in the air. The nitrogen signal doesn't change during the reaction because the pressure doesn't change too much. And that remains pretty constant. But you can use that as an internal reference for the oxygen band. And that allows you to follow oxygen evolution and hydrogen peroxide decomposition. You can see that they correspond very well. So that's a little aside. So when we follow the reaction, and I'm looking at time, I haven't got too much time, Colin, but I'm almost finished. We look at this reaction and we see there's something odd about it. Nothing happens for the first 4 or 5 minutes, and then all the hydrogen peroxide gets decomposed to oxygen. And we get a little bit of conversion of alkene, and that's not quite what was reported. If, however, we mix the scandium and the complex together, go for lunch, a nice long lunch in the Netherlands, 60 minutes, then come back again, add the hydrogen peroxide, nothing happens for the first 4 minutes, but then we get pretty decent conversion, 25% in this case, and all the hydrogen peroxide decomposes. This is not a fluke. This is highly reproducible. There is a standing time, which determines the efficiency of the reaction. There's an induction time, and then there's a reaction time. So this is not a simple reaction as you would think. Question is, what's happening? Well, very briefly, I'm going to flash quite a few Raman spectra in front of you in the next minute or two. We can get Raman spectra of this complex, and we can do O18 labeling, which allows us to assign bands. So we can actually take a solid sample as complex of 785, get a Raman spectrum, we can make the complex with O18 water during the synthesis process, but it doesn't exchange with the complex in solution, but you have to make it with O18. So we can actually identify which bands are related to manganese oxygen and which are related to manganese nitrogen structures. So we can assign these bands. We can also calculate the structure and calculate what sort of shifts we expect. So you see that on the left, on the right. So if we take the complex of 785, 1 millimolar, it's too low a concentration to be observable by Raman spectroscopy. If, however, we move to 355, we hit into a metal to ligand charge transfer band, ligand to metal charge transfer band, so it's oxo to manganese. Well, if we compare the spectra, we actually see that there's the appearance of 2 new bands. All the rest of the bands aren't there, but 2 new bands which appear at 355 that are not present in the same solution at 785, so these are resonantly enhanced. And if we zoom in there, you actually see more clearly. You also see the signal to noise is a bit better at 355 than at 785. That has nothing got to do with Raman spectroscopy. That just happens to be how often you acquire and how much you average your signal and so on. So this is purely experimental settings why there are difference in signal to noise. So if we follow by UV vis what happens when you add scandium to the complex, you see very dramatic changes in the absorption spectrum over 80 seconds. If you follow the Raman spectrum over the same period, you actually see there's very large changes to the Raman spectrum as well too at 355. So there's something happening in the complex. But if you note that those changes take 80 seconds, I'll come back to that, about 80 seconds, they're not instantaneous. You can see really clearly there's one band which goes down, another band goes up, and one band goes up very strongly in intensity. If we add water or add O18 water, everything goes back to the original thing. So we reset. And then remember, when you add hydrogen peroxide, you're adding a 50% solution of water. So there's always a lot of water added, an excess of water. So actually, once the hydrogen peroxide is added, the complex goes back to its original state. So the scandium has actually done nothing permanently. We calculated the shifts we expect with scandium, and they didn't match what we got. And that raised a question, what is the scandium doing? Now, it's a good thing to read the literature. We always say in a group, 2 hours in the library saves you 2 weeks in the lab. So if you read the literature, you actually see the scandium triphlates are prone to hydrolysis to release triflic acid. That's an easy one. So we add triflic acid instead of scandium, and we see more or less the same behavior that we see with scandiums. Triflic acid also works, and triflic acid is a Lewis acid. More than that, if we look at the absorption spectrum, we see that the changes are not over 80 seconds, they happen immediately. And if we look at the Raman spectrum, we get the same changes that we get with scandium, but it actually matches what we calculate for protonation. Now, why is scandium having this effect? Well, if we think back, and I assume you haven't read my paper, so you have to take this as true. Adding an acid to this complex shifts its redox potential to a redox potential which is close to what hydrogen peroxide can do in terms of reduction. So hydrogen peroxide is known as an oxidant, but it's actually a reductant as well. It's isoelectronic with hydrazine. So the adding a proton makes it easier to reduce this complex. And actually the 4,4 complex is kinetically very inert. You have to reduce it to a 4,3 or a 3,3 oxidation state before you start getting ligand exchange and you can form an active form of the complex. Triflic acid and scandium triflate have exactly the same effect on the redox chemistry of the catalyst. In fact, it makes it much easier to reduce. So where does that leave us? Well, it's a very short, there's actually a much longer story to this, but I've just tried to highlight the spectroscopy sides of it. What does it tell us about scandium and how it works? Well, the reactions, and as reported, are entirely reproducible. I have to give credit to Mike Watkinson. I had a good bit of discussion with him. I mean, this is a very reproducible reaction. It's actually quite a nice way to get the catalyst to work. And adding triflic acid to reactions is painful. It's a nasty substance, but adding scandium triflate is actually quite nice. But the reality is, scandium triflate is involved as a source of triflic acid and not as a direct coordination to the metal center. So it's not acting in the same way as in photosystem 2. It's actually acting just as a source of triflic acid. And it's the protonation from the triflic acid which is leading to the activity that we see. Now, there's implications for many other Lewis acid activated systems which are reported in the literature. If you look at them, it is very likely because of the conditions that are used, especially for oxidation chemistry, they're actually looking at Bronsted catalysis. So, give you a few conclusions, and sorry for going a little bit over time. I hope to show you that monitoring reactions in real time can give you information which is essential to understanding how your reactions are working, how the complexes that you're using or the catalysts you're using are behaving. And it's important to use as many different spectroscopic techniques as you can, but also, especially with Raman spectroscopy is not one technique. There are many flavors of Raman spectroscopy, and if we use, for example, resonance enhancement, and we go for very high time resolution, we can actually get information which is not really accessible by any other approach. And the key thing about Raman spectroscopy, and I'm a very big proponent of Raman spectroscopy for this reason, you get structural information in real time. So UV-vis spectroscopy is very useful for following the changes that happen, but the structural information from Raman spectroscopy is second to none. Now, I give you a quote. Not everything you see is important, and I think it's Yuval Harari, and I think it's actually I've forgotten the name of the book as well. It comes from A Brief History of Humankind as well too. Today, power means knowing what to ignore, and I think one of the difficulties with reaction monitoring we face now, especially when you get large amounts of information, is you may be able to see things, you see species, you see features. A difficult thing on reaction monitoring nowadays is knowing what actually tells you something about the reaction and what are things. For example, these nice absorption bands we were seeing in the first system. They're nice, they're interesting, but they have nothing got to do with the catalysis. So in understanding reactions, knowing what you can ignore is an important power as much as actually being able to see things. So with that, I hope I've given you some insight into reaction monitoring. I realize it's very brief, and I have to thank a few people. Dunpen Unyaran is a Thai student who was in my group a few years ago. She's currently in the south of the Netherlands working in a company on research. And you see here, I think it's in San Francisco we were when we took this photo. And Jorn Stein, who's a Frisian student, so Dutch, and he's finishing off his PhD, and he worked on the manganese. And you see some of the students in the group and some colleagues, and me dressed up because we do PhD defenses with style online in the Netherlands nowadays. And I have a few people to thank, especially from the theory side I didn't mention, as Maya Gruden in Belgrade, especially, and Marcel Swart in Girona. And of course, Hans de Boer and Roland Haag at CatExcel. And for funding, the Functional Molecular Systems, it's a government program in the Netherlands. And of course, the cooperation with industry, for example, with Axo Nobel, is on the Advanced Research Center for Chemical Building Blocks. And thank you for your attention.
Thank you, Professor Brown. Excellent talk. Now, we can attribute some time to allow for some questions. And just a reminder, please be sure to type your questions into the question box in your control panel. So, Wesley, I'll start with one. So Raman is an inherently weak phenomenon relative, say, to using a more coarse method like absorption spectroscopy. So in that context, I know you can use you have used resonance Raman to enhance the signal, and that works really well. It gives enormous enhancements of signal, but it still is a relatively weak phenomenon. Does that impose any time resolution restrictions in reality when you're trying to follow catalytic processes? I know it's not an easy thing to answer in a black and white fashion, but in practice, does it typically impose time restrictions on, or time resolution restrictions that you wouldn't necessarily be faced with by using absorption techniques?
I think a few years ago we would have said yes, that you're limited to 4 or 5 second time resolution. What I showed you there in the first example, that was actually a relatively simple setup. It boils down to, can you get your optical collection right? So every photon counts. And it's not just having the best camera and spectrograph. You also have to think about how the light comes out of your sample, the field of view of your lenses that you're using. It's really, to some extent, when you want to push the limits, you really have to make use of every photon, collect everything you can. Sometimes putting a parabolic mirror behind your sample actually improves intensity by a factor of 2 or 3. And a factor of 2 or 3 in intensity can make a big difference in limit of detection. So typically for systems, we're looking at about 10 millimolar limit of detection for normal Raman spectroscopy, but I think we can go down lower. At some point, you get hit by shot noise and things like that. So I think the limit now is things like fluorescence from samples, which give you shot noise, which will ultimately limit the detection limit you have. But actually, for the very fast reactions, our problem is mixing. It's not even the Raman spectroscopy anymore. It's how fast you can mix. And we have used stop flow with Raman spectroscopy, and bubble formation and mixing has been our challenge rather than the actual time resolution of the Raman system. So I reckon 10 milliseconds it should be achievable as a time resolution for normal systems, normal organic systems in this period.
Mm-hmm. On the mixing front then, is that more of an issue for Raman than it would be for standard stop flow absorption?
Yeah. So if you take absorption spectroscopy or IR or near IR spectroscopy, you have a very, very large spot size if you think about it. So the actual beam of light coming through your sample is very large. So it gives you very much an average of what you see.
Mm-hmm.
Raman spectroscopy is, well, it's nice and confocal, intrinsically confocal, but that means you have somewhere between 10 and 50 micron spot size. And that's a very small spot on a solution where you have eddy currents going and you have solvent moving around. And the consequence of that is you really can actually see things moving around as eddy currents in your solution, whereas with IR, near IR, or UV vis, you can quite happily ignore them. One approach around this is to use a very long focal lens and actually essentially just use a zero focus system. And if you can cut off the low wave number region and you're happy to do that, then you'd probably be able to get a very large spot size.
Mm-hmm.
But most of the efforts towards getting large spot size in these things usually mean you get a massive drop in efficiency.
Mm-hmm.
So in the end, it's keep your volume small. Keep your volume almost as small as the confocal volume or the field of view of your sample, and then you should be fine.
Mm-hmm. I have another question here. If we overlap with solvent bands, can we simply do a scaled subtraction, or does that have consequences?
Yeah, in principle, yes, it's quite easy to do a scale subtraction. There's two problems with that. The first is you increase your noise by a factor of 1.4 because you have noise in both spectra. And the second problem is your refractive index of your material does change when you start adding things into it. And that refractive index will cause small shifts in the optics, which will start illuminating different parts of the CCD. So you get a small shift in how the CCD is illuminated. And you get this kind of derivative effect when you start doing solvent subtraction. There's not really much solution to that. And our experience now is really just to stop. As a group, we've stopped doing solvent subtractions routinely. I think years ago, that was the standard thing you do in analysis. But actually, to be honest, if your band is if you have an overlapping solvent band, one trick is just to use a deuterated solvent and move it and hope you're lucky. But subtraction is really, because of the refractive index changes that you can have happening in your solution when you start adding different ingredients to it. If you're working at very low concentrations and your refractive index is not affected, probably you get away with subtraction of solvent bands. But my experience is if your bands of interest are away from the solvent, don't bother subtracting, just do a baseline.
Right, okay. We're almost up in time, but I'll squeeze one more quick question in. So I noticed quite heavy use of 785 nanometers. So near infrared Raman, was that more to step away from fluorescence? Is fluorescence often a very real background limitation?
And these systems actually was inner filter effect is a problem. These catalysts absorb in the visible. And for one of the catalyst systems, we actually used 1064 to do resonance enhancement because it absorbs out in the near IR. And you get very nice resonantly enhanced spectra of 1064. But your solution also boils very quickly because an absorbance means you absorb the energy. And if you're using a 200 milliwatt laser on a very small volume, you get a very rapid heating of your sample because of absorption. So even if it's a solution, you do get heating of your sample. So the reason for using 785 is typically just to avoid issues of inner filter effect or sample damage by heating. So you minimize it. The more you go into near IR, the more you go into the near IR absorbance. So 830 and 1064, 900, those wavelengths, you start hitting into overtones in the IR. So even though you don't see them when you run an absorption spectrum, you do actually absorb light vibrationally, and that means heating of your sample. And that can affect your kinetics dramatically. So the reason for 785 is kind of the happy medium between everywhere. 355 is actually a very, very useful wavelength for reaction, for avoiding fluorescence. 400 nanometers tends to be a bit dodgy in terms of encountering fluorescence, but 355 in our experience is one of the most used wavelengths sometimes in the lab.
And then you must get a big Raman signal intensity boost as well from the wavelength of the Power4 effect.
Yeah, so you can. We've a 10 milliwatt system, and the 10 milliwatt will give a higher signal to noise than a 300 milliwatt 785 system. So it's just yeah. So it is a massive. And if you go to 266, you go down to the half a microwatt or half a milliwatt. But then you get into fluorescence issues, and 213 you can go down to 10 microwatts or 20 microwatts. So it's, but then you get into the expensive laser systems. So if I was given the system, just buy a 785 system.
Fair enough. Thank you, Professor Brown. So I think we're all out of time in terms of questions. I should tell you though, I mean, if you're listening on demand to this, you can still type questions and they will be answered offline. So thank you very much for your attention to him, for all your questions. Massive thank you to Professor Brown for this excellent talk. A recording of this webinar will be available in Andor's Learning Centre on andor.oxinst.com from next week. Please be sure to check out the website and get in touch if you have any further questions. Thanks again for joining us today, and please enjoy the other presentations on offer.